Neumann. He is a professor of algebra and geometry in the University of India in Italy, and he will talk about a very interesting topic about the hidden secrets of mathematics. And you can see the title 1 plus 2 plus 3 up to so on, which is, we know that in the mathematics is a divergent series, but it still can be written as is equal to minus 1 by 12. It is very surprising. So now we want to see that why this is true. So welcome, Professor.
First of all, thank you very much for the very kind invitation. It's a great pleasure to be here at last. And I'm sorry that the stay is over on Sunday. But maybe when someone flying and have to stay.
Yeah.
So thank you very much. The talk I'm giving you is part of this John Conway Spirit seminar series. So I tried to follow the spirit of Conway, so I know I will say it in any sense, because nobody can give such inspiring talks than John Conway did. If you ever have seen him in life, it's a really surreal experience. But I also would like to link this a little bit to the course I was giving here during the 2 weeks on complex analysis. So this will be really an analysis talk, so I'm not an analyst, say this. And but I hope at the end of the talk I will give you some ideas about some recent research I'm working on, which is a bit related to this work. Okay, so the title, as you see, looks a bit paradoxical. 1 plus 2 plus 3 plus 4 plus 5 is minus 1 12. And if I tell this to you, normal days in the first or second year of studies, you would say, this man is doing math. How can this be possible? But actually, yeah. So the question is, we want to listen to it, and it's actually a question physicists ask a lot. So, what is the infinite sum? 1 plus 2 plus 3 plus 4 and so on. Does the infinite sum have a value? This is our question. Now, if you are a student, an honest person, let's say, you're a math student, then you would of course say, I hope everyone of you will agree, in particular the students, that no, this infinite sum is a divergent series and therefore has no limit. And in fact, it goes over all limits, so it should be zero. Okay, and if this is all what I wanted to say, then we can all just go home, but let me make a comment. If you're a reckless cheat, so this means you are either a maths professor, theoretical physicist, or string theorist, then you, of course, will say, obviously, the answer should be minus 112. And so, how is this possible? So before I come to the conclusion, let me say that you might think, how do physicists come to this sum? And you have a problem?
Yeah. Very good ones.
I don't know how to do that. I don't know how to change the map. Is it possible? Okay. This is already, I think, the highest level. The mic is here. Okay, so I hope I can see the screen. Okay. Is it okay? Can you hear me? Okay, so let me continue. So why physicists believe that this is minus 112? So let me first give you. I cannot change the. Okay. So let me give you an example. This is a physics book, a modern physics book.
The sound is really poor. I can't seem to hear anything. Has the lecture started?
Can you hear me now better? Somebody on Zoom?
Yeah, now it's better.
It's better.
Yes,
Yeah,
Yes.
now it's clear. Thank you.
Thank you. So the technicians, but now I cannot. Excuse me. Can you please put this away? Yes. I cannot How can I put this this away? I need to take this away. The Neumann should not be there. I want to take this away. Right. Yeah, now this doesn't work. I cannot change this. Okay, so let me come back to this slide. So I said, of course, if you're a math student, then of course you know that this infinite sum is significant series, so there cannot be a value, right? But if you're a physicist, then you are obviously sure that it should be minus 112. And you might think, okay, how is this possible? So that's one of the first things I want to explain to you, why this value minus 112 might be the right value for this series. And also turns out that this value is not any value, it also has a geometric meaning, and I will say something about that at the very end. Actually, it's the Euler characteristic of a moduli space, a space which classifies elliptic curves, which is very important in algebraic geometry, in particular in number theory. So I'll come to that later, I will say a little bit about that. But first, let's convince ourselves that this minus 112 might be actually the right value for this. And that you believe me that I'm not saying some fantasy things here. Here's a physics book, in fact, a book on string theory, a recent standard textbook on string theory. And if you look at this, you can see here, forget about the rest if you're not a physicist, but at some point you get to calculate some energy amount. So at the end, you get something like this, and there comes up the sum of all natural numbers from 1 to infinity. And then here it says that, doing a certain type of renormalization, this leads to the odd result that this goes to minus 112. So they do some kind of what they call renormalization. So that's the magic word in physics, in theoretical physics. And this allows you to get rid of infinities. So that's a very standard procedure in quantum field theory and string theory. So let me just mention, this is around for a long time. Classically, I put some names here. Oppenheimer, Feynman, of course, who did these Feynman diagrams, and others. When you look at universal theory of forces like weak force, strong force, and so on. For example, I put also here Weinberg and Salam. In fact, Salam was one of the first person who developed the renormalization theory for meson theory for certain type of particles in I think in the 50s. And so these procedures to get rid of infinities, which you get when you sum up in energies, is very, very important. And you see this sum naturally comes up in some very concrete physics problems. And also in string theory, so I put some other names here, we didn't let us. These things also there come up. We have very often infinities you want to get rid of. Okay, but let's come back to the basics of real analysis, or complex analysis. So if you, of course, know that any sequence of real or complex numbers, and then you can look at the associated series, then of course you know that we have a clear definition when something is convergent with a limit or not. Of course, we know that a series is convergent with a limit if and only if the associated sequence of partial sums converges to the limit. So in other words, you take the partial sum, that's the first k numbers of your infinite sequence of complex or real numbers. And those sequences, you get a sequence should have a limit, and the limit should be L. No? That's exactly what I'm saying. So the infinite series has a limit L if and only if the sequence of partial sums converges to the limit L. I think we all know this from a book. If not, then you should recall this from classical calculus real analysis course. And of course, otherwise, we call the series Lippergeld. It has no limit. Yeah, let me give you an important example. You all know, just to warm up a bit, so the geometric series. Yeah, so if you have two numbers, A and R, either real or complex numbers, which have a certain line, a certain domain. So either the opens in the complex plane in the open circle of radius 1 around the origin, or which just has absolute value between -1 and 1. Then, of course, we know what the infinite series of the form A times R to the n from n to a to 0 to infinity is. So that's, of course, basically, if you calculate this, you can calculate the limit. This is A divided by 1 minus R. No? So you have to show that the sequence of partial sums converges. I think we all have hopefully done this. Well, you know what the limit of the sequence of partial sums. So you can write this down. This is a plus ar is plus ar squared and so on plus ar to the k. The a is just a constant. You can take it out. So you have this sum to deal with, and we know that the limit of that. Yeah, so you can write this first of all as 1 minus r to the k plus 1 divided by 1 minus r, and then you take the limit for k goes to infinity, and this will be a divided by 1 minus r, because if you take the limit of r to the k plus 1 for k goes to infinity, then this is 0, in particular for this domain of values of r. No? You can just write this formula easily. So that's an easy exercise normally when you see this in the calculus books. So the geometric series, which is very important for many applications, and for example, if you plug in numbers, so should be value should be smaller than 1. Put 1/2, you get 2, and if you take 1/4, you get 4/3. You can see this here on the slide. And okay, this is an important example. And then now let's come to the physicist series. Yeah? The infinite sum from 1 to infinity of 1 plus 2 plus 3 plus 4. You take the sum of our natural number. This is of course divergent. Yeah, it's obvious because what's the sequence of partial sums? Well, it's just this sequence of sk, the case element of the case partial sum. What you get is just the sum from 1 to plus 2 plus 3 plus k, which is just 1/2 k times k plus 1. No? I can put this by induction, or just pairing numbers the way Gauss did already long time ago. And of course, you know that those goes over all limits. So this goes to infinity when k goes to infinity. So this sequence of partial sums for this series does not converge, and therefore there is no limit of the series. Okay, so then you might ask, so how do you resolve the physics result in this? Okay, we come to this later. But I want to give you another important series, which we'll see later in other incarnations. If you take the infinite sum of the harmonic series, so it's just the infinite sum 1 divided by n. Yeah, so it's 1 plus 1/2 plus 1/3, which is very important in music theory, for example. No, that's why it's called harmonic series. It was already studied as the Lorentz. You can read this. Well, and of course we know that it is divergent, and you normally see a neat proof in your calculus class. But let me give you an argument of a French mathematician in Neumann, Nicole Oren. I think he lived a long time ago. And he, of course, had no limit modern mathematics at his hand. So he was arguing as follows, which I think is really nice. And you see that there were a lot of clever people around at that time already. So if you take the sum of all these, yeah, 1 plus 1/2, so it's just identified, then you can pair certain things. You can pair 1/3 plus 1/4, and so on. And then you can pair these two numbers, and you can take the next four numbers, 1/4, 1/6, 1/7, 1/8. And then what I do is I replace them with the smallest. Yeah? So in the first two pairs take 1/4, then I have these four, the smallest one is 1/8, so I replace all the others by 1/8, and you can imagine the next one, how many will I have? I will have 8, right? And I can replace them by 1/16. And if you do this, then of course, if you put this all together, you get all 1/2, and you sum up infinitely many 1/2, and obviously this goes over all bounds, and so it's clear that this cannot converge now. So we see that the sequence of partial sums does not converge, as we have for each integer. Yeah, if you think about this, you can write this down formally. So the partial sum S2k from n equals 1 to 2 to the k of 1 divided by n is always greater or equal than 1 plus 1/2 times k. And of course, if k goes to infinity, this goes to all bounds. So no change. This is harmonic series is divergent. Here's another series, which was studied by an Italian mathematician, Grandi. The infinite sum of alternating ones. You take 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. Is divergent. Yeah, I think we believe that also. Yeah. But of course, you could think at the time people were a bit puzzled by this series, because if you take here, for example, you can take parentheses. 1 minus 1 would be 0, plus 1 minus 1 would be 0, plus 1 minus 1 would be 0, plus 1. Yeah, if you put parentheses here, you will get 0. But if you start with 1 and then you put these together, you will get 1, right? That's already strange. So why is that? Because these people at the time didn't really know how to deal with infinities. Yeah? So, but we can now show, of course, that this is a divergent series. Yeah, we just have to check the sequence of partial sums. So for even k, so k is 2l, we see that this will always be 1. And if k is odd, so like 2l plus 1, then you will get 0. And you see, you have two accumulation points, yeah, but they're different, namely 1 and 0, so they cannot be having the same limit. So this the sequence of partial sums does not converge, so there's no limit. Yeah, so this series was discussed by Guido Grandi in the 17th, 18th century. Here's another example. We take not the physicist series of the sum of all natural numbers, but we take alternating sum. 1 minus 2 plus 3 minus 4 plus 5 minus 6 is also divergent. And you can just check what the sequence of partial sums is easily. Yeah. You see that the sequence of partial sums is 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, 5, minus 5, and it goes in all direction negative. There's no chance this can converge, right? So the sequence is not converging. So again, this sequence of partial sums does not converge. So this infinite sum is also divergent. And now a physicist comes along, said, no. Leave me alone with all this formal nonsense. You know, anyway, it's first year mathematics. I know much more. So no, okay. I don't care about divergence. We shall have this for the following infinite sum. So in fact, he takes Grandi series of alternating ones, summing up, and says, well, the value should be 1/2. The alternating sum of the sum of natural number, all natural numbers should be 1/4, and then finally the series I've already mentioned should be minus 1/4. Let me give you an argument of this, a physicist's argument. And okay, let's take the first infinite sum of ones. If you think about it, doing it the physicist's way. So if we calculate the partial sums, we have seen we will either get 1 or 0, depending if we stop after even or odd steps, right? So the sum could be either 0 or 1, and both appear with the same probability. So let's just take the average. Right, we take the average of 1 and 0 and divide by 2, then obviously you get 1/2. So the sum should be 1/2. And that's what physicists do, they average over experiments. So I'm doing an experiment here, we see whether we just take 1/2. What about the second one? The alternating sum of natural numbers. Okay, so I multiply it with itself, or add it to itself. If I do this, I get 1 minus 2 plus 3 and so on, plus 1 minus 2 plus 3 minus 4 plus 5 minus 6 and so on. And if I do this, I get 1. Then I add minus 2 plus 1, I get minus 1. Plus 3 minus 2 is plus 1, and so on. And you see what you do is you recover Grandi series, which we have already calculated. This was 1/2. So therefore, we have for the second sum, sigma 2 is 1/2 of sigma 1. It's 1/4. Okay. And now finally, we can do our third sum, the sum of all natural numbers which come up in this renormalization problem I mentioned from the string theory book and elsewhere. Okay, what I do is I subtract the second infinite sum from the third one.
There's no sound again. I think we've lost the sound.
I don't know, somebody is working on the sound. I'm not sure what is happening. Yeah, sorry. That's beyond my control, I'm afraid.
Yeah, the sound is back. Can you do this slide again, starting from the third sum minus the second sum?
Is it better now? Can you hear me?
Yes, we can.
Okay.
Yes, we can.
Okay. So
But can you? Yeah. Thank you.
No problem. Yeah, sorry for the technical problems that is related to the microphone, but let me know when you can't hear me again, so we will fix. Okay, so we have seen sigma 1 is 1/2 and sigma 2 is 1/4. What about the sum of all natural numbers? So the argument, okay, would be subtract sigma 2 from sigma 3. If you do this, we have 1 plus 2 plus 3 and so on, minus 1 minus 2 and so on, and if you sum it up, of course you get 0, because 1 minus 1, 2. First of all, you get 4, then you get 0, then you get 8, 0 with negative sign, we subtract, and 0, and so on. Now, to do this, you get 4 plus 8 plus 12, and so on. To take out the 4, and you get, again, reproduce the series 1 plus 2 plus 3, sum of all natural numbers. So I can say this is 4 times sigma 3. And then we get 3 times sigma 3 is minus sigma 2, and therefore sigma 3 is minus sigma 2 over 3, which is minus 1/12, which means that the sum has the value minus 1/12. Okay, and now you might think, so that physicists are happy with this argument. No? And what would you think? Is this a good argument?
I think the average part, in the first round when you took the average, I think there might be some problem in taking that.
Yeah. for example. But also here you have a problem because you work with infinities and you just play as they would be finite sums. Of course, we all know if you're an honest mathematician, this makes not much sense. It's nonsense. Even though the results seem to be justified. So let's see how we can make sense of this. So this, what I showed you now, is not a proof. Forget about this. And in fact, it was put on YouTube at some point by some clever mathematicians who said mathematicians don't get enough hits on YouTube. So let's put this proof up. And immediately there was a lot of discussions, and they got a lot of hits. And and they got it's very clever because people get talk about mathematics. That's all what we want. Normally, nobody talks about mathematics, no. So we're not on TIC or whatever. So obviously, it makes sense to do. So they were very clever. Of course, then everyone realized mathematician, well, this is nonsense. Makes no sense. This is who cares? These are the right numbers I want, and that's fine. Okay, and famous here. Let me just cite a very famous mathematician, Niels Henrik Abel. He said that the divergent series are the invention of the devil. And it's a shame to base on them any proof whatsoever. I think he's right, we will agree. By using them, one may draw any conclusion he pleases, and that is why these series have so many fallacies and so many paradoxes. Right, so now the question is, for us as mathematicians, just want to use this now, we're going to use them daily, can we make the physicist argument rigorous and associate actual values to divergent series? Physicists have wonderful ways of using mathematics, and sometimes mathematicians, the string theory is one big example, had a lot of impact in mathematics. So it was really important to find the right mathematics input here. So the rigorous, and it is sometimes very hard. So physicists are always a bit ahead. And so we have to follow and make things rigorous. Okay, so how can we make this rigorous? So there are many rigorous mathematical methods to deal with these infinities and divergent series, and actually associate actual value to them. So the question should not be what is the limit, because we know there is no limit for these divergent series, but the question is, can we associate a value to these divergent series? Right? Those are two different questions. No? Yeah, as I said, this plays an important role in also number theory, complex numbers and mathematical physics. Physics we have already seen. So let's look at some methods of how to make this rigorous. It's actually not so hard. So if you take, again, the sequence of real or complex numbers and its associated series, then we could slightly modify the definition of a limit of convergency. And this is an idea due to the Italian mathematician Ernesto Cesaro, another Italian, and when they come out, I didn't choose them, but he was one of these persons who came out with this in the 19th centuries. We call a series Cesaro summable with Cesaro sum L if and only if the average of the associated sequence of partial sums converges to the limit L. So we don't take the sequence of partial sums and look for a limit. We take the average of the partial sums, the sequence of partial sums, and then see if it converges. And if it converges, we call this limit the limit of the Cesaro infinite sum. So what we do is formally, we let n go to infinity of the average. We take the partial sums here. We sum up the partial sums from 1 to n, from the sequence of partial sums, and we take the average. And then, you want that this limit exists, and this limit L is in the value of the sum. So in other words, the Cesaro sum of an infinite series is the limit over n of the arithmetic mean, or what we normally call the average, of the first n partial sums of the series. Now let's see. So I give you this as an exercise for those who want to do some homework over the weekend. So if you have a series which is convergent with the limit, standard way, you can easily show that it's also Cesaro summable with Cesaro sum L. So what we show is that this notion of value associated to the infinite series is more general than convergency. So you can call this Cesaro summable or Cesaro convergency if you want. We wouldn't want to use the word convergency because it's not convergence. I just associate a value which is basically the limit of the averages of the sequence of partial sums. And you can show that if you have already a convergent series, then it's also Cesaro summable, and the Cesaro sum is the same as the limit. So you haven't lost. If you talk about Cesaro summable series, you have a larger universe which allows you to deal with situations like this, for example. Now we can now make this argument which the physicists did with averaging, make it precise, because we can take this infinite sum and we can easily see it's Cesaro summable with Cesaro sum L equals 1/2, because the sequence of partial sums of this series is 1, 0, 1, 0, 0, 1. And we get a sequence of their arithmetic means, which looks like this. 1 divided by n, sum of k equals 1, n of the partial sums. If n is even, we see we get 1/2, no? If you add this up. If n is odd, then if you do this, you get L divided by 2L minus 1, depending on what the position is. But now if we take the limits for the first one, so all these sequences should have a limit, and they should be the same. Well, the first one is constant, you get 1/2. And for the other one, you get L divided by 2L minus 1. For L goes to infinity, this is also 1/2. So the value is the same, and we see that this is our sum is 1/2. And so you see, we can use the Cesaro technique to show that this Grandi series has actually a nice value, namely 1/2, which is the one that physicists also want. Now, here's another exercise for you. You can easily check that if you take the alternating sum of natural numbers and also the physicist series of the sum of all natural numbers, it turns unfortunately out they are not Cesaro summable. So this technique of Cesaro will not work to give a value for these other two. So we have to do something more ingenious. And to do that, we go back to a genius, namely Niels Henrik Abel, who basically invented the method of Abel summation. And this goes back to, I have talked about this in my lectures on complex analysis, you use the theory of power series. You can do this in a complex situation or in the real situation. So what's the idea? The idea behind this is Abel's famous theorem, which you probably have seen in a course in real analysis or complex analysis, I hope. But let me just recall it. If you have a sequence of real or complex numbers, then what you can do is you can associate or you can add another variable, call it z, which should normally be a complex number, but it could be also be a number, call it x. For me, z is either real or complex, so it's like a variable you put there, and instead of taking the series itself from n equals 0 to infinity of an, we take the series n equals 0 to infinity of an z to the n. For fixed values of z, we can see this as a series, right? And we have now the freedom we have introduced the freedom, namely the variable z. So that's the associated power series. If I give you a sequence of real complex numbers, you have an infinite series and you have an associated power series. Now, the theorem of Abel says, suppose that the original series of complex real number is convergent with limit L, then I can recover this limit by just taking the limit of the function gz, where z goes to 1 from below or within some domain. So I write it here now in the real way, but so this is just, well, z goes to 1, and then it's just the value L, which is just the limit of the series. So z is a real variable, or if you are in the complex plane, for my students, then you have to look at a certain region, which is called the Stolz region, which lies within a complex open unit disk. So in all z have absolute values smaller than 1, such that you can find a capital M. So you have some kind of boundedness condition that 1 absolute value of mine minus z is smaller to the m times 1 minus absolute value of z. M is supposed to know. Then it also works in the complex case. So this is a general case of our theorem in the complex case. So basically what it says is, we don't look at the series, we look at the power series and then interpret the limit of the convergent series as the limit of the function. Okay. Now think about something where you don't know it's convergent. So you might not have a limit, but we could still take what we could do is we could still take the power series and try to see what happens. Maybe the limit was that 1 exists from below. And then if it's a value, we say, okay, the original series doesn't have a limit, but we say that this will be the value of the limit. No? And if you have a convergent series, then Abel's theorem tells me that's exactly the limit of the convergent series. So Abel's idea is to replace the infinite sum of all these with this associated power series. So it gives me more freedom, as you have seen, and then see if the limit from below, for z goes to 1 from below, if you are on the real axis, exists. If this limit exists, then we call the series, the original series, Abel summable, with Abel sum being this limit, which is coming by taking the power series. And basically what Abel's theorem then says is that each series which is already convergent with the limit L is also Abel summable with Abel sum L. Here's another exercise for people who have a lot of time. You can show that any Cesaro summable series is also Abel summable with Abel sum with Cesaro sum. So if you have a convergence series, it's Cesaro summable. If you have a Cesaro summable series, it's Abel summable. So Abel's machinery is even more general. So now let's see if we can use that to get some nice values for the other two theories. So let's first take what we have already seen. We know already this was Cesaro summable, but can we also see that it's Abel summable? It should be, because that's what this, I didn't prove it, but that's what it's stated. But we can check it on this particular example. Now, if you take the Grandi series, it has the following associated power series, which is always convergent for absolute value of x smaller than 1. One, you can also take it on the complex plane. It doesn't matter. So take the real case here. So yeah, let's write it down. You can write it down now. The power series, associated power series, minus 1 to the n, x to the n, and then you sum it up. Now, if you write this in formulas, it is 1 minus x plus x squared minus x cubed plus x squared minus and so on. But you know that this has a limit. So this is 1 divided by 1 plus x. So it's 1 divided by 1 minus x. And we put minus x here because of the negatives. This is a standard thing we have seen already for basically coming from the geometric series considerations. Okay. Now I want to see what is the Abel sum. So I let x go to 1 from below. Yeah, and so I take the limit for x going to 1 of this power series. So that's just the limit for x goes to 1 from below of 1 divided by 1 plus x. Well, this is 1/2. The value, the limit of the function is 1/2. So we see that's exactly what we have already observed during the Cesaro summability. So Abel's summation method gives me the value 1/2. Now let's look at some other strange infinite sums. So obviously this looks like, now we can play with this. We just sum up once. I mean, obviously that's not convergent, right? We just sum up once. And if you look at the associated power series, then you get the geometric series. Yeah. So you get 1 plus x squared plus x cubed plus x fourths, and we know the value is 1 divided by 1 minus x for all x which have a certain convergence radius, meaning that the absolute value of x is smaller than 1. That's our classical analysis. Now we can, and then we know that it behaves very well, so we can take differentiation on both sides. So we can take on the left to take d dx of this series, which is converted, so no problem. And if you do this, then you get the series 1 plus 2x plus 3x squared plus 4x. This is just standard analysis. I'm just simplifying it now, but we know that you're allowed to do that. And using, you can think about this sum 1 plus x is just like an infinite polynomial, and you can do it in all cases, and everything works well. You can do in analysis normally to justify that you can do this. So if you take the differentiation on the left side, you get this series here 1 plus 2x plus 3x squared plus 4x cubed and so on. And on the right hand side, we should get the same thing. Yeah, so we should differentiate the right side. We can use the quotient rule of this function, and then you get 1 divided by 1 minus x squared. And therefore, we have that the sum 1 plus 2x plus 3x squared plus 4x cubed is 1 divided by 1 minus x cubed. So we get immediately the value for this series. Now we look at the infinite sum, which we see we couldn't do with Cesaro summability. But let's see if we can do Abel summation for this one. No? So alternating sum of natural numbers 1 minus 2 plus 3 minus 4 plus 5 minus 6 and so on. So it's the sum of n equals 0 to infinity of minus 1 to the n and plus 1. So what's the associated power series? It's exactly the one, more or less, we have here. So what's the associated power series? We get 1 minus 2x, so it's just another, there's a sign here, plus 3x squared minus 4x cubed plus 5x 4 minus 6 is 5 and so on. And the value is 1 divided by 1 plus x cubed. So it's exactly that. Now we have to put minus x here instead of x, and then you get 1 plus x squared. So we know that this power series has this value, and then of course we can use Abel's summation, and we let the limit from x go to 1 from below. If you do this, so limit for x to 1 from below, it's just the limit of x goes to 1 from below, or 1 divided by x, 1 plus x cubed, 1 plus x squared. That of course is 1/4. 1 divided by 2 is 12 is 1/4. So we see the value is 1/4. I have justified now the second series. And Euler already was puzzled about these methods and had already an intuitive idea. He didn't have all the formalism at the hand, which we now have since the 19th century and so on, using epsilon delta and all these things that you learned in calculus. But Euler already observed that this is quite funny. So he said, when it is said that the sum of this series 1 minus 2 plus 3 minus 4 plus 5 minus 6, etc., is 1/4, that must appear paradoxical. So by adding 100 terms of this series, we get minus 50. You can check the first 100 terms, you will get minus 50. However, if you take the first 101 terms, you get plus 51, which is quite different from 1/4, obviously. That is clear because it does not converge, right? And becomes still greater when one increases the number of terms. But I have already noticed at the previous time that it's necessary to give to the word sum a more extending meaning. Yeah, infinite sum doesn't mean necessarily it's convergent, then you have a limit, then we are fine. But the question is, what value can I associate a finite value to it or not? And our summation method or Cesaro summation method allows us to do that. And we have seen that ours one is the most general one. Now we can finally consider the infinite sum of all natural numbers. The one we are really after. We want to show it's minus 1/12. To do that, I have to introduce some trick. We use another summation formula. Our summation formula is not working here. And so we have slightly modified things. And this is what we call zeta regulation or zeta function regulation, which somehow is indirectly due to Euler, but then of course to Bernhard Riemann and Srinivasa Ramanujan, who discovered many interesting relations. And he had already an intuitive idea for this in the 20th century. Okay, for this I have to introduce a very important function, the Riemann zeta function. Now, this is a very nice function. It's a function defined on the complex plane, first of all, I mean, for complex numbers, so you can write them as sigma plus I theta, where sigma and I are real numbers. So this is the standard of the easy way of writing S as a complex number. And I can write down a series and I take the analytic continuation of the series on the complex plane. And so what you get is sigma S is the sum of n equals 1 to infinity of 1 divided by n to the S. So it's 1 divided by 1 to the S plus 1 divided by 2 to the S plus 1 divided by 3 to the S and so on. Or I can write it in this form as an infinite sum 1 to the minus S plus 2 to the minus S plus 3 to the minus S. Yeah, and you can take fixed S, you get some infinite series. And so we can vary S, it gives you a function. It gives you a function, not a power series, it's something more complicated because the variable is in the power. That was the ingenious idea of Riemann. And you see, then you can check, and I have no time to do this here, it's something normally you would do in analytic number theory, or hopefully my students in complex analysis will see by one of the later lectures, that you can actually find a nice function on the complex plane. Well, you have to be really careful what you mean by this. So we want to have an analytic continuation of the series. First, you have to make sure when does this series actually converge. Well, it is always convergent for all complex numbers which have a real part. Yeah, so this is my sigma greater than 1. For all real part greater than 1, we know it's convergent and you can extend it. So, in fact, Riemann proved that, and that's normally what we do, proved that the zeta function is a meromorphic function on the whole complex plane, which means the following: it is holomorphic everywhere on the complex plane, except for a simple pole at S equals 1, and there it has a residual 1. So that's standard complex analysis. So, the Riemann zeta function, given as a series, can be continued on the complex plane, and it has nice values besides S equals 1. And what do you get for S equals 1? Just there. You put S equals 1, but you get the harmonic series, and we have already seen it is dim again, and there's no way to put any value to the harmonic series. The harmonic series has a nice, but it's really a bad in the sense that it's dim again. So that's the pole of the function. So S equals 1, I get a pole, not the function. So this Riemann zeta function, of course, as we all know, or probably have seen or heard about, is one of the most important and famous functions in all of mathematics, because it has a direct link with number theory. In fact, with the propagation of prime numbers. So, for example, we have the following statement: Riemann zeta function is of fundamental importance in number theory because it can be shown to be the following so-called infinite Euler product. So basically, instead of the definition I have there as an infinite series, yeah, one can actually show, and Euler basically showed that, not all the arguments, but then Riemann make all this very precise. Turns out this is actually the product over all prime numbers of the expression 1 divided by 1 minus p to the minus s. Now, if you write this product up, what I mean by this is just as an infinite product of these factors, 1 divided by 1 minus 2 to the minus s, 1 divided by 1 minus 3 to the minus s, 1 divided by 1 minus 5 to the minus s, the next one will be 1 divided by 1 minus 7 minus s, only for primes, yeah? Put only primes. And actually it's nice, because you can use this, if you believe this, and you have seen this, but this requires a proof, of course, nothing falling from the sky, you have to work hard to do this, but it's not so hard, if you know the standard methods, you can prove this. And for example, if s is equal 1, then we know that the left-hand side, yeah, this infinite series is a divergent harmonic series. Yeah. And it follows from the right-hand side, yeah, if you have this infinite product, that there must actually be infinitely many primes. Because if there would, so this gives me an analytic proof that there are infinitely many primes. You have probably seen Euclid's proof that there are infinitely many primes by contradiction, but this is direct proof, analytic proof basically, because assuming that there are only finitely many primes, then this product on the right-hand side would be a finite product, and you will get a finite value. Yeah? But if so this product 2 divided by 1, 3 divided by 2, 5 divided by 4, s equals 1. Yeah? You get the product of p divided by p minus 1, prime number divided by its predecessor. So you get 2 divided by 1 times 3 divided by 2 times 5 divided by 4. Now, if you have only finitely many primes, you have only finitely many factors. The product is finite, so you have a number, a finite number. Let's say we have 1 billion prime number, and not more, we will get some finite number. But we know on the left-hand side, the thing is divergent, the series, so there cannot be a finite limit. So there cannot be finitely many prime numbers, there must be infinitely many prime numbers. So another proof, one-line proof that there are infinitely many prime numbers. But let's not get distracted. Coming back, we have to see what is the sum of 1 plus 2 plus 3 plus 1 so on. Well, let me just mention that the Riemann zeta function also satisfies a nice functional equation. For all s complex numbers besides the origin and 1, we have this nice functional equation. So it looks very nice. So zeta of s, yeah, we can relate zeta values of the zeta function, namely zeta of s and zeta of 1 minus s in this way. So there's a factor here, 2 to the s, pi, the number pi, s to the minus 1. Then we have a trigonometric function. Yeah, it's really like a sine pi s divided by 2, and then the gamma function, which is another important function, 1 divided by 1 minus s. Now, if you look at the equation, function equation, I will not prove it here, but for example, if you put in s is equal minus 2, minus 4, minus 6, minus 8, so we take the negative even numbers, and you see because you have the sine function there, that zeta of s is always 0. And these are called the trivial zeros of the zeta function. You get them automatically. So we have infinitely many, which are coming from the even, which are given by the even negative natural numbers. Yeah. But using the Euler product, one can also show that the zeta function is non-zero if the real part of s is greater than 1. Yeah, so when you have a complex number which has a real part which is greater than 1, it cannot be a zero of the zeta function. And then, of course, the question is, where are all the zeta, the zeros of the zeta function, the zeros of the zeta function? Well, and this is a famous statement or hypothesis by Riemann, the Riemann hypothesis. She raised in 1859 or something like that. So that's a conjecture. It's unproven. It's one of the most important conjectures in mathematics because, of course, it relates to many interesting questions in number theory, as we have seen, the relation between prime numbers. And also it's one of the millennium problems. So if you solve this, you will get $1 million, but I should warn you, many people have tried, it's really hard. And many very smart people have tried. So anyway, let me just remind you of the Riemann hypothesis that we are talking about, the Riemann zeta function. Yeah, it says the following: the real part of every non-trivial zero, so the trivial zeros were the ones which you get for even negative even numbers. The real part of every non-trivial zero of the Riemann zeta function is 1/2. So for all s, which are belong to z minus 1, such that s is not equal to the even negative numbers, it follows that the zeta if zeta of s is 0, then the real part should be 1/2. In other words, the non-trivial zeros of the Riemann zeta function are all lying on the critical line 1/2 plus I tau, where tau is anyway known. So that's a very important conjecture.
So can you give me understand that?
What did you not understand?
That trivial and non-trivial zero.
Yeah, so if you, okay, so thank you for the question. So if you have this functional equation, which I haven't proved, so you have to believe me now, but you can work it out. You see there is a sine function here, pi times s divided by 2. If I put these even numbers there, the sine function will be 0. So for all even negative numbers, you get a setter of this s is equal to 0. So these are the so-called trivial zeros. You always have them. Easy to see. Now the question is, what other zeros you might have of the setter function, right? And then Neumann made this hypothesis, this conjecture that if you take any non-trivial zero, non-trivial means not one of the ones which of this form. No? So any ones which are not equal to -2, -4, -6, which is not a negative even number, then it follows that the real part, so S is a complex number, and it follows that the real part has to be 1/2. So whenever you have, it doesn't tell you where they are, but it tells you that they will lie exactly what the numbers are, but it tells you where they lie. So they lie on the critical line 1/2 plus I tau, where tau is a real number. So you see there on the real part is 1/2. So you can draw a line from the complex plane, and that's where they lie. And then, of course, number theorists have worked hard to find some of them. And so far, they all lie on this line, but nobody has proved this hypothesis yet. Okay, but now let's go back to our famous series, our problem. The physicist is 1 + 2 + 3, and so on is -1/3, which is used in renormalization in quantum field theory, gauge theory, and string theory, and so on. Right. So let's take the zeta function. It's now we know we have convinced. I hope I have convinced you this is a well-defined function on the complex plane. It's a meromorphic function. Has a pole at s = 1. So I can take the zeta function, I write it down. So actually I should take the left-hand side, zeta. So the right-hand side is basically just writing down what it means. It's this infinite sum. Now what I can do is I can multiply the zeta function. It's a well-defined function. Yeah? So there's nothing vague here now. I can multiply the zeta function with the following term: 2 times 2 to the minus s. 2 to the minus s is another function well-defined, and 2 times 2 to the minus is another function well-defined. So I can multiply the function zeta s with this function. It's a product. And then I do the following. I take the first line, subtract from it the second line. I get 1 minus 2 to the 1 minus s of zeta s. Yeah. And if you write this down, this is the alternating. It's an alternating sum of these zeta values. 1 to the minus s, minus 2 to the minus s, plus 3 to the minus s, minus. So that's a variation of the Riemann zeta function, which was studied intensively by Dirichlet, and that's why it's called, it gets a name. It's called eta of s, which is called, it's a so-called Dirichlet eta function, which was introduced by Peter Gustav Lejeune Dirichlet. In fact, it was, I should say, Riemann was a professor in Göttingen, a successor of Gauss, and of course, he died quite young, and then Dirichlet took over, but then also he died very young. So he was also professor in Göttingen. So I'm very happy about that because I did my PhD in Göttingen. So there's a long list of famous mathematicians. So I feel very humbled to be in this line. By the way, Oppenheimer also did his PhD. The physicist, so a lot of physicists did PhD in Göttingen. It was one of the centers of mathematics in the 20th century, and it's still a great mathematician. Okay, so we take 1 minus 2 to the 1 minus s zeta of s, and we get this alternating version of the Riemann zeta function. We call this eta of s. And this is what's called the Dirichlet eta function, and it's also a well-defined function. It is meromorphic function and so on, has nice properties and so on. You can study that one. And it turns out that it's sometimes easier to study Dirichlet eta function than Riemann zeta function. Okay. Now what we do is we have this equation. The relation between the zeta function and the eta function. Yeah? So 1 minus 2 to the 1 minus s of zeta of s gives me this eta function. Now I take for s equals -1. I can do that. Now the function is both functions are well defined. So I can take s equals -1. If I do this, I get 1 minus 2 to the 1 minus s. Okay, what do we get? We get -3. And then zeta of -1 to the left hand side. On the right hand side, I have eta of -1. Okay, so I get this equation. Yeah. Evaluation on -1. So let's write this now again in explicit form. -3 times zeta of -1 is equal to eta of -1. Now if I write this as infinite sums, then of course I would get -3 times the infinite sum n equals 1 to infinity of n. Now this is exactly, yeah, you see for if you take the zeta function for s equals 1, sorry, for s equals -1, you get exactly the sum of natural numbers. Yeah. And there's a value there because the function is defined. So what is this value? We can now calculate it. So we take -3 set of -1 is eta of -1. So this is -3 times the sum of all natural numbers. On the right-hand side, eta of -1. So what's the eta function? So this is the alternating sum. If you put s equals -1, you get 1 minus 2 plus 3 minus 4 plus 5 minus 6. So that's the alternating sum of natural numbers, which we also have, see, which was 1/4, right? We have already found the value. And then, okay, so we write this in this form, I get this. But we have already computed the value of eta of -1 using Abel's summation. And so finally, yeah, so remember, we have, okay, so we have -3 times eta of -1 is eta of -1, which was given as the limit for x goes to 1 from below of this power series. Yeah, remember, this is what we did. And then we have seen that this is using geometric series, it's the limit of x to 1 from below of 1 divided by 1 plus x squared, which is the limit, which is the value of this infinite series. And we saw that this was 1/4. Now we see that -3 of zeta -1 is 1/4. Now we divide both sides by -3. We can do this in a well-defined equation. We can divide by -3, which gives me the desired value, because if I take, so zeta of -1 is -1/12, but zeta of -1 is exactly the value of the sum of all natural numbers. So I have now shown you that you have a nice value for the sum of all natural numbers, and it should be, as the physicists had already told us, -1/12. Okay, so now let's come to the other part. Remember, I said this little statement that this is also the Euler characteristic of some geometric object. So I have about 5, maybe 10 minutes. I start a bit later, no?
Yes, sir.
Yeah, so let's look at this from a different angle. So with this, we need a bit of language. Question? Hello? Somebody talking? No? Okay, let me continue. So let's have another look at all this from a different angle. So for this, I need to introduce some language which is also useful. Of course, not so much time. So this is a language of category theory. So very often you want to count things, and it turns out you want to count things with symmetries. So maybe you have some bijections or isomorphisms of some algebraic objects or so on, and then you come naturally to the notion of a category. So let me say what is a category, very basic. So a category is basically, in some sense, you want to generalize the concept of sets, and it actually is another way of four foundations of mathematics. So this was developed by Adam McLean in 1945, and basically, what is it? So it's given by a class of objects. I don't say set here, to don't get into some set theoretical problems, but you can make it precise. You pick a class of object. If you just think about some object. I will give some examples. You have object and you have morphisms, which we call maps or arrows. So each morphism has a source object and a target object. No? Normally, when you have a map, you start somewhere and you go somewhere. No? You have a source and you have a target. And you can write this as an arrow from A to B. No? And then you can take the set of all morphisms from A to B. You can always get all the arrows you have. And then you have a composition normally of morphisms of maps. You can compose them. If you have a morphism which goes from A to B, and you have one which goes from B to C, then of course you can compose the two, and you go from A to C. Yeah? And then you want to have that this has some natural axiom, then it should be associative. Yeah? So it doesn't matter in which way you compose, where you put it. And of course you have an identity, a special morphism, which is identity, which just maps any object to itself. Yeah? And this, of course, acts like a unit. It goes ways from right and left. Yeah? Two-sided unit on any morphism. So, and then of course, if you have a category, you can talk about functions which are the source and the target function. So it goes from the maps, the morphisms, so C1, to the objects, C0, by just doing the following. If you have a map, you can take its source, which is A, where you start, and you can take its target, where you end, which is B. Okay. So normally we can also write internally a category in the form C0, which is two source and target maps. Well, it's just a notation to indicate that you have objects and morphisms. So a category is just objects and morphisms. Let me give you some examples. Take the category of sets. Yeah, so the objects are all sets, and morphisms are function between sets. Not very interesting. That's without any structure, but nevertheless, that's a category. You can easily check that the axioms are flattened. More interesting, if you do linear algebra, you come along finite dimensional, say, vector space of the real numbers or some other field, complex numbers or finite, whatever. Anyway, you can make a category out of this. the objects are finite dimensional vector spaces, and morphisms are just the linear transformations. They take care of the structure, namely being vector spaces, while for sets, of course, there is no structure. You have some extra condition. In algebra, you study groups, of course, fundamentally, the objects for studying symmetries. Now you can take the category of with objects groups and morphisms, group homomorphisms, which take into account the group structure. If you have a morph, it's not just a set map between two groups, but it also has to take into account the multiplications on the two groups. That's a category. Or, more interestingly, you can study the category of rings. You have more structure, with an addition and a multiplication. So you can talk about the category where the objects are the rings and morphisms are ring homomorphisms. And now let me give you a very particular category, which was introduced by a German mathematician, Brandt, who's completely unknown besides this introduction. So he worked a bit on algebraic number theory and came up with this very interesting notion. He says that, okay, if I want to study some mathematical object, I want to study it together with the symmetries. Symmetries means like automorphisms of it. So I would like to have them together. And you came up with this notion of groupoid, which somehow generalizes groups and sets at the same time. Now, what is this? So groupoid is a category, in the sense I've just defined, in which every morphism is an isomorphism, or automorphism. So in other words, every morphism has an inverse. Yeah. So if you have an arrow from an object A to an object B, then you have one the other direction from B to A, such that the composition gives the identity, which is a morphism in your category, both ways. No? It's invertible in both ways. Let me give you an example. Every set gives a groupoid. The objects are the elements of the set. I give you a set, finite or infinite, I don't care. The objects I declare are given by the elements of my set. And there's only one morphism, namely the identity morphisms. I just put one artificially. I just say there's an identity morphism from X to X. There's no other symmetries. It's just like you put points, and this points visualizes an element of my set. And that's a groupoid. And the source and target maps are just identity morphisms. Yeah, so that is a very simple example, but already you can take a group, it becomes more interesting. If you have a group, then you can define a group. We call this BG for reasons I will not explain, but those who know a little bit about the theory of stacks will probably be happy with this notation. Let's now, I have given a group, and now I build a group with a different thing. It's a category, and I take only one object. I call it star. I have only one object. I call it star. But I take as a set of morphisms all the elements of my group G. Now, the group G has an algebraic structure. You can multiply and you have inverses. So what it means is that if I take as a morphism the element group, I can compose them. The composition is just group multiplication. And each element has an inverse. So this means all morphisms are invertible. So I get a group. And the objects, it's just the object. The class of object is just the singleton, it's just my one object, and the class of morphism is my group G, identical to group G. And the source and target maps are just trivial, and composition is just group multiplication. So this is a group. Let's do something more interesting even, which combines sets and groups. What we do with groups, you let them act on something. You let them act on some set. No? That's what you do in combinatorics for some. You have an action of a group, you want to understand the symmetries. So let's have a group acting on a set. So it means that you have a function from D cross X to X, that is a product, which means that you can multiply an element of X with an element of the set X with an element of D. What does it mean? You let the element of G act on this element X. So yeah, it's kind of a translation or whatever it could be. You have seen group actions, maybe linear algebra and group theory. Yeah. So any group action gives on a set gives me. So we have done such a function such that, of course, it has this nice property with respect to the product of two elements. And of course, if you take the multiplication with an element, with the neutral element, you do not this X left event. Then we can cook up the groupoid, the action groupoid, which looks like this. So the objects are just the element of my set X. And for any two elements in X, we can find a morphism which corresponds to every element G such that G times X is Y. So an element Y is given by an action of an element G of an element X. I get a map, a morphism from X to Y, which is just given by the multiplication. So I take the set of all these morphisms in this way. And, this defines me again a group width. You can easily check the answer. Explicitly, yeah, so we have this group width here. So the objects are X and the morphisms look like G cross X. So they look all like elements from G times X. So the source map is just maps everything to X, and the target map maps everything to G times X. To the value. And we see composition exists whenever we have Y is equal to G times X. So you can compose two of these elements, H comma Y and G comma X is H times, you can just multiply H times X. You act with the product of the two elements. And you can do this because Y is G times X, so you can act with another one. So this is valid 5. This gives me a group width, it's called the action group width. In particular, here's an example which is quite important also, which comes up in everything when you want to identify things. And not just by identity, but by some equivalence relation. It comes very often. We have seen this quotients. Every big quotient you need an equivalence relation. Topology, for example, quotients. And if you take a set with an equivalence relation, so what does it mean actually? Well, if you write this formally, you say equivalence relation means that each element is in relation to itself, and if X is in relation to Y, then Y is in relation to X. And if X is in relation to Y, so that's basically symmetry, and then we have transitivity. So if you have X, Y is in relation, X and Y are in relation, and Y and Z are in relation, then X and Z are in relation. So that's an equivalence relation. Now I can build a group width where I take again as object the elements of X, and then the morphisms are coming from my relation in the following sense that the source map is just mapping everything to X, and the target maps to Y, and composition is given whenever you have a relation. So X comma Y can be composed with Z comma V, and it's then X comma V. Whenever Y and Z are in relation, I can just use the axioms of an equivalence relation. So this gives me another example of a group width. So these are very important constructions, group actions and equivalence relations. Basically, if you understand these two, you understand all of mathematics actually. Come up in many different areas. You have a differential manifold, you have an algebraic variety, with some algebraic group acting or Lie group act or whatever, and you get naturally to this. Now let me give you a very stupid example, but not actually that stupid. But you take the group width of all finite sets. So I only allow finite sets, not any sets, but just finite sets, meaning have finitely many elements, and bijections between them. So the morphisms are bijections, and the objects are finite sets. So bijections are one-to-one and quantum functions, so bijections. So in some sense, you can say that group widths have symmetries and take into account the symmetry. And so let me now say a little bit about, if you have a group width, you can talk about the automorphism group of an object. If you have an object, then its automorphism group, so given an object X, its automorphisms are all the invertible arrows from X to X, they form a group because you can compose them. This is called the automorphism or isotropic group of my group. So for each object, I also get these groups, these automorphism groups, which basically describe my symmetries internally. So let me do an example. If you take a set and then take the associated group width, where the morphisms are also the set, so it was a very trivial example, then for each object, there's only the identity, because the objects were just the element of my set. So I have only the identity. So the automorphism group is the trivial group. If I take the example of a group and the associated group width BG, well, then there's only a single object, but what's the automorphism group? This got all the elements of G. So the automorphism group is my group G I start with. So I've just basically the same data, I've just written it in a different way. More interesting, if you take the group action on the set, then for each object, what is the automorphism group? Well, that's just the stabilizer group with respect to the action, because you can see that these are all the elements in G such that G times X is equal to X, and this is exactly the stabilizer group. So you get all these classical notions from group theory in this way also. This is the automorphism group of an object in the action or transformation group. Now, if you take the set of finite, the group width of finite sets, then if you take a finite set, let's say with n elements, so a finite set has a number of finite elements, so let's say it has n elements. What is the automorphism group? These are all the permutations, bijections of a set with n elements. That's my symmetric group of order n. Okay. Then I can also talk about connected components or isomorphism classes in a group. Now, basically, it's given by all objects which are connected by an isomorphism with another object. So we can talk about the set of isoclasses or the set of connected components of a group. And we normally write this as pi naught of G. It's just a notation. Yeah. So for each object I can take its component that lies in some component like this. And you can easily show that it's a nice exercise for any two objects of a group which are in the same connected component, their automorphism groups have to be isomorphic. Yeah, so in some sense we can say a group is something like a group with many objects. In fact, yeah, so a group is just a group with one object. You know, remember it was just one object and the morphisms are the group G. But in general, you have more objects. So in fact, also you could take disjoint unions of groups, which also give me a group. So you can actually use group to do study group theory. I'm not going to do this. Now let me remember when you normally do this, you have a set, for example, a finite set, you talk about the cardinality of a set. That's just the number of elements, right? And if you have infinitely many elements, you just say the cardinality is infinity. Okay, we can do the same thing for a group we can talk about the group cardinality or the cardinality of a group but this is a slightly different count because a group is basically objects together with automorphisms or symmetries. So we have to count the objects together with the symmetries. So what's the right way of doing cardinality for group weed? Cardinality of a group weed is the following real number. You sum up over all the objects by taking isoclasses. So I can just take one representative of any isomorphism class of my group weed, because they all have the same automorphism group. And then I take the absolute value of the automorphism group of that object and take the inverse of that. You might ask, okay, does it make sense? You know, definitions are neither true or false, they're useful or useless. Let me show you that this is useless, very useful, very useful. Okay, so the sum is taken over all isomorphism classes of objects, and the absolute value is the order of the automorphism group of the object. Now, this is an infinite sum, maybe, if you have infinitely many isoclasses. So this might not converge, same problem. So it might not converge. So if this sum diverges, we say that the grouping cardinality is infinity. Let me do an example. If X, oops, should be careful with the microphone, kind of walk away. So let X be a finite set, and let G be the associated group with. Well, how many isoclass? Well, you know, each element of my set gives me an isoclass. And how many automorphisms do I have? The automorphism group is just the identity group, yeah? So the trivial group. And so the grouping cardinality is just the sum over all the elements in X, which is just the order cardinality of X. So for a finite set, I recover the original cardinality of a set. Also for the infinite set, I get infinity. So you get basically nothing new. Yeah? So the cardinality of a set is a special case of the cardinality of a group group. So I've generalized this. If you take a finite group, then you have, of course, the group width has only one object, so there's only one isoclasses. And we know what the automorphism group is just G. So you see the group width cardinality in this case of the group width associated to a finite group, say, is just the inverse of the group order. And the other case, if you have a group action on a set, finite, let's say we have a finite group acting on a finite set, then you can take the action group width. And then you can easily see that, I give it to you as an exercise, that the group width cardinality, which is given there, we take the automorphism for each isoclass, is just a fraction, the ratio of the cardinality of X and the order of T. That's a very nice formula. We have seen Burnside formula. Yeah? So this is normally only true for we take the quotient group, and we take the ordinate space, then you only know that this is true for free action. But if you take the group width cardinality, this makes even sense if the action is not free. So the group width is a very good replacement for the quotient when the action is not free. And you get a Burnside type formula. So using group width is really useful. Now, let's do a very funny example. That's getting to the group width of finite sets. So the objects are just finite sets and morphisms are bijections. Sets. What is the group width cardinality? So, okay, so I have written here. So we take here representative of isoclasses and then divide the automorphism group. Now, each finite set is isomorphic to the set of n of one set with n elements. You can take the normally it's written the set 1, 2, 3, 4, 5, 6, 7, 8 to n. Or you can take those and start with n equals 0. And then, what is the automorphism group of such a set? So the others are all isomorphic. If you have a set of finite of k elements, it's isomorphic to the set 1, 2, 3, 4, 5, 6, 7, 8 until k. So only pick those as representative, if you like. And then, okay, this sum here is just the sum over all natural numbers, including 0. And then you have to take the automorphism group of such an element. So what is the automorphism group of a set with n elements? As I've already said, that's just the symmetric group of order n. So you have to take the order of the symmetric group here. So we have to divide, we take the sum of n in n0, 1 divided by absolute value, of the order of this n. And what is this? Well, this is n factorial. So what we get is the infinite sum of 1 divided by n factorial, and we all know this is E. So you see the group width cardinality of a group width can actually be a real number. Can be so what is the, so in some sense you can say what's the number of finite sets and its symmetries? Well, the number is the transcendental number E. So we see we get very often now not natural numbers anymore. We can get rational numbers very often, or we can even get real numbers. And here's an exercise for you, a nice exercise. So I'll leave it to you with an interesting question. Play with it. I give you a real number R. Can you construct a group width which has a group width cardinality R? Okay, now I come back to, I'm over time. So let me just say a little bit about the geometry at the end. So we want to study elliptic curves, and in order to do so, we can actually want to find a space. Elliptic curves play an important role in number theory, arithmetic geometry, we studied for a long time. They are very important. And of course, if you want to study them, you would like to have a so-called moduli for classifying space. Again, the idea going back to Riemann, which means that you have a space where the points correspond to symmetry types of elliptic curves. So how do we construct such a moduli space of elliptic curves? So very briefly, let me do this here. We take the upper half plane of the complex plane. So these are just, you see, just take the imaginary part greater than 0. And on that, we let operate a nice group, namely the so-called special linear group, which is, but we do it over the integers, so basically like a lattice operation. So it's just given as the set of all matrices, the values of this form. It should be symmetric joint, and the determinant should be AD minus BC is equal to 1. So we take this special linear group, which you have seen in linear algebra probably with real values or complex values, but now take integer values. I can do that. No, okay. It's a ring, so I plug in the ring, we get a group joint. So we let the group acting on the upper half plane via the so-called Möbius transformation. So I haven't done them in the complex analysis course yet, but hopefully the other lectures will do it later. So you have a nice way of making transformations of the upper half plane by using these this special linear group. So for each matrix and point in the so each matrix gamma and the point in the upper half plane, I have a transformation, and I just tell you what is the new complex number in this form. So it's A theta plus B divided by C theta plus D. And this gives me a nice transformation. And then I can take the quotient of that. In fact, you have to take the quotient with respect to the symmetry. So I can take the group weight actually. And in fact, it gives you a geometry. You can make it into a very nice geometric object, which is called a quotient stack or orbifold. I'm not going to define this here, but you just think about this, which will give you a good idea of what it actually is behind it. You can actually use that transformation or action as a good way. And this space then classifies elliptic curves, and it's also called the moduli stack of elliptic curves. And let me just say that elliptic curve, of course, has a canonical form. So these are like given by cubic equations, cubic polynomials of this form, 2 variables, and they should be non-singular, so the graph have no cusp or 7 sections. So here are some examples of parametrization in this Weierstrass form. So these are typical examples of elliptic curves, and you want to take the moduli space of all of them. And here's a picture, a nice picture of the action of SL to Z on the upper half. So there's a lot of geometry going on here, which I have no time to talk about. But I would like to say, what is the relation to this minus 112? Now, if you have this moduli space of elliptic curves, you want to study it. So you want to know, do you find some algebraic invariance of that? And yes, you can. You can see it as a space, and you can do the Euler characteristic, for example.
which if you have a polyhedra, yeah, like a cube, you can take the vertices minus edges plus faces. So if you take, for example, a cube, yeah, then you get 2, now because you have how many vertices you have? You have 8, right? How many edges do you have? You have 12. And how many faces do you have? You have 6. If you take the alternating sum, you get 2. It's not surprising because it's like a convex polyhedra, and they always have the values. You can also take the tetrahedra, they all have this problem. This was an idea of Euler to get some invariant of some geometric shape, topological shape. And you can in fact generalize this. If you have a compact topological space, then you can define the Euler characteristic in all dimensions, not just in dimension 2 or 3, by just taking alternating sum of certain dimensions of vector spaces, which are given by the so-called singular cohomology. So those of you who do the course in topology, point you will see the definition of CS coefficients. These are just vector spaces. For each I, you get a vector space and they have a dimension. And these particular ones were introduced by Betty a long time ago. And for example, if you get the sphere, you can check that the Betty numbers are 2, and this is not surprising. It's the same as convex polyhedra, because you can think about a sphere as a deformation, a continuous deformation of a polyhedra. In topology, you don't care. You can always continuously deform. You don't care about metrics. So you get the same number. And more generally, for these quotient stacks, you can of an action of a group on some variety, let's say, you can also define an Euler characteristic, but it takes also into account the symmetry. So it's a kind of more general version of this classical Euler characteristic. But nevertheless, you can do that. So you have to take into account all the stabilizers, and then you can calculate this Euler, so-called orbifold Euler characteristic of this moduli space, and it turns out that it's exactly zeta of -1. Therefore, it's -112. So you have